Hello everyone, I'm going to present our ECCV 2022 work towards realistic semi-supervised learning. This work has been co-authored by me, Mamshad Naim Rizvi, Dr. Navid Kardan, and Professor Mubarak Shah. And as we all know, supervised learning relies on large level data sets, and constructing large level data sets is expensive. Semi-supervised learning, on the other hand, only requires a small level data set, and it's one of the fundamental problems in machine learning. Now let's look into open world problems. Generally, the models we deal with are closed walls, and the closed wall models require knowing all classes in advance. However, we constantly encounter new classes while exploring an unconstrained environment. A practical model, therefore, should be able to properly detect and handle new situations. Therefore, researchers have explored different research directions. For instance, there are methods called open set recognition, where the objective is to identify novel class samples during inference. And in open world recognition, the goal is to detect and incorporate unknown samples into training. So this is basically a human in the loop approach. And there is new set of methods which are called novel class discovery method, where the objective is to use seen class information to cluster novel class samples. In this work, we are basically combining these two notions. That means we focus on a problem called open world semi-supervised learning. In here, we'll be given a set of labeled data, which is very small, of seen classes, and we'll have a set of unlabeled data where we'll have samples from those seen classes, and we'll have also samples from new classes or novel classes. For instance, we now have samples from the class frog, class dolphin, and class zebra. So the objective of this task, that means open world semi-supervised learning, is to classify samples from the seen classes, that means the class elephant, octopus, and cheetah, and also to cluster the new classes we have encountered in the unlabeled data, that means the class dolphin, zebra, and frog. So the objective of this work is to classify novel class samples and to improve known class performance by utilizing unlabeled known class samples. So the major contributions we make in this work are the following. We propose to apply Singhorn-Knopp to unify the entropy maximization and pairwise similarity loss based training as done in the prior work. We introduce an extension of Singhorn-Knopp that handles arbitrary prior distribution of classes for more practical application of our method. We propose uncertainty guided temperature scaling to improve reliability of pseudo-label based training. Finally, we introduce a method to estimate the number of unknown classes so that our method can be applied to more practical setup. So from high level, our method has basically two parts. One is pseudo-label generation, where given unlabeled data, we pass it through the network, and using the class distribution prior and Singhorn-Knopp algorithm, we'll generate pseudo-labels. And once we have the pseudo-labels, we perform reliable training with the now labeled and pseudo-labeled data, and in the reliable training phase, we'll employ uncertainty guided temperature scaling and train the model using a single cross entropy loss. Now let's look into our class distribution aware pseudo-label generation. In our work, we generate pseudo-labels for all the unlabeled data, and once we have the pseudo-labels, we can train the model using the ground truth labels and pseudo-labels using cross entropy loss, and it's pretty straightforward. But generating pseudo-labels for unknown classes is a complex problem because we know only very little about those unknown classes. Therefore, we have to inject some kind of inductive bias in this work. And in this work, to be particular, we are using class distribution bias for our pseudo-label generation. So what it does is basically, if we know the number of samples in a particular unknown class, what we are looking at that the generated pseudo-labels for that particular class should actually follow the same distribution. That means the number of generated pseudo-labels for a particular class J should be equal to the number of samples in that particular class. And this constraint pseudo-label generation problem is basically a transportation problem, which makes our job easier. Now let's look into a simple example of transportation problem. In this case, we have data about some cheese producing problem. We have different farms with different milk producing capability, and we have different artisan shops which has a different amount of demand for that milk. And given a cost metric, which is basically the distance from the farm to the cheese shop, The goal of the transportation problem would be to satisfy the demand of those artisan shops while incurring the minimal cost. We can draw the same analogy for our pseudo-level generation problem, where given some samples and some samples and some classes, if we know the number of samples that has to be assigned to a particular class, in here we are showing in the blue row, and given the initial probability output from the network, the goal of the transportation problem would be to satisfy the demand of those classes while making minimal changes to these output probabilities. So in a formal way, we can express this transportation problem by matrix. That means transport matrix A, which has to be member of a transportation polytope, which shape is basically the number of unlabeled samples nu and the number of classes. And if we look into the details of this transport matrix A, we can see that if we are summing across the across the rows, and now if we we'll be left with a vector. Now if we look at the vector and for each j, we'll see that the number of pseudo levels will be equal to the number of samples present in that particular class. That means nu cj. And if we are summing across the column, it should sum up to 1, since these are probability distribution. The division by nu is to make the transport matrix a joint probability matrix. So how do we optimize that? The optimization of this pseudo-level generation, or that means the determining the transport matrix A, is basically this term, where the minimization problem is that A being a member of the transportation polytope. The trace, we have to minimize the trace of A transpose multiplies by the log of the output probabilities. If we look at this simple example in here, we're looking into a two-dimensional output, and if we go through the product log and product between the A transpose and the output probabilities, we can see that this equation is basically doing a cross entropy between the transport matrix A and the output probability y. The only difference is in here is, instead of optimizing or optimizing the output probabilities, we are trying to optimize the transport matrix A, given the constraint that it is a member of the transportation polytope A. So let's say we have the optimization problem, but our task is not solved yet. Now, if we remember it, we have the information about the class distribution prior, but the problem is that we don't know the particular order of the unknown classes. So even if we have this excess, we don't know what would be the permutation or in what order we will have to apply this class distribution prior. So in our work, we come up with a permutation matrix P pi, which dynamically aligns or permutes the data and the permutation matrix during the optimization step. So this is our final class distribution aware permutation or class distribution aware pseudo-level generation minimization problem. So we solve this minimization problem using Singhorn algorithm. So from high level, what it does is, given some unlabeled data, we pass it through the network and generate some initial pseudo-levels. And in here we are looking into ideal example where, let's say, we have 4 classes C1 to C4, and the first 2 classes are known and the last 2 classes are unknown. And generally what happens is the samples will get assigned to these known classes, but we want some of the pseudo levels to be assigned to the unknown classes as well. So after applying our class distribution prior and Singhorn, we can see that we'll have the final pseudo levels where some of the pseudo levels will get assigned to these unknown classes as well. Now let's look into our reliable training. So in our training, we are using pseudo levels which are being generated by employing the output probabilities. Therefore, the final performance will be affected by the reliability of those pseudo levels. And this pseudo level reliability can be improved by incorporating uncertainty. Therefore, in our work, we generate different augmented versions of the input to obtain predictive uncertainty. There are other ways of doing it, but this is cheap and simple. Therefore, we basically perform Monte Carlo sampling to measure or get a notion of this uncertainty, which basically looks into the variance of multiple stochastic forward passes done by different augmentation. And once we have the uncertainty, now the question is how do we actually use that? So basically what we can do is we can filter some of the samples based on this uncertainty score, but that would be very sample efficient. So instead in this work what we do is we introduce uncertainty over temperature scaling. So we apply this dynamic scaling term, which is basically the uncertainty score, into the softmax probability computation. So from high level, if we look at it, this would have been our typical softmax probability scores of different samples. Now, since we have the uncertainty information of the samples, and in here we are basically putting a lighter color for lower uncertainty and darker color for higher uncertainty. And after our uncertainty guided temperature scaling, what we can see is that if the uncertainty is low, the output probability is more sharpened now, and if the uncertainty is high, we'll basically flatten the output probabilities. That means the example we see in the last row. And now here is our overall method. Given some access to the unlabeled data, we want to generate pseudo-labels for them. So for that, we first create two augmented versions of those unlabeled data. Then we pass both of the augmented version through our neural network, and using the class distribution prior and Singh-Hornov algorithm, we get the initial pseudo-labels from them. Then from those initial pseudo-labels, we perform cross pseudo-labeling to enforce consistency between these two transform versions. That means we'll swap their pseudo-labels. Then from those cross pseudo-label, we'll basically generate our final pseudo-label through mixed pseudo-labeling. In here, what we are trying to do is we are trying to encourage confident learning for novel classes. So basically, if the confidence of the prediction on any of the novel classes is higher than certain threshold, we'll make that as a one-hot prediction. So this will be our final mixed pseudo-labels. Now we'll basically pass the label data and the two transform version of the unlabeled data through mix-up augmentation, and we'll have our mixed input. Then we'll pass it through the network and get the initial output probabilities, and we'll perform our uncertainty guided temperature scaling for reliable training. And once we have that, we'll basically we'll have to think that we did mix-up augmentation on the input, so we'll have to do mix-up augmentation on the output as well. That means mix-up between the final pseudo-labels and the ground truth labels for the label data. Then once we have the output mix-up, we'll basically compute cross-entropy loss from the network output and the mixed output we have. Here is our overall training algorithm. For input, we'll have a set of label data, we'll have a set of unlabeled data, and we'll have access to the prior class distribution row, and we'll have the iterations per epoch E, also the maximum iterations for the full training K, and the temperature T. And it will output the trained neural network FW. At the beginning, we'll initialize the neural network FW, and we'll initialize the set of uncertainties for the label and unlabeled data with the temperature T. Then for iterations up to K, we'll sample a batch of label samples, and we'll sample a batch of unlabeled samples. Then we'll perform the Singh-Hornov algorithm and using our class distribution prior, and we'll also perform the cross pseudo-labeling to swap the labels between the two augmented versions of the unlabeled data. Then we'll perform mixed pseudo-labeling to obtain our final pseudo-labels. Once we have the final pseudo-labels, we'll perform mix-up augmentation between the labeled and unlabeled data. Then based on the cross-entropy loss on those mixed inputs, we'll update the parameters of our network. Then for after every E epochs, or that means every E iterations, that means end of the epoch, we'll compute the uncertainty of the samples. And finally, it will actually return the trained network FW. Now let's look into some results. In here, I'll show results on 3 data sets, which are CIFAR-10, CIFAR-100, and ImageNet. And for these experiments, we are assuming the 50% classes are seen, and the remaining 50% classes are novel. And of those 50% seen classes, we'll only use 10% data as labeled. So on this CIFAR-10 data set, we see that our method outperforms the previous state-of-the-art method, ORCA, by more than 8%. We see higher improvement on CIFAR-100 data set, and we also see a very noticeable improvement on ImageNet 100 dataset. In here, we perform experiments on tiny ImageNet dataset, and we can see that even on this dataset with more number of classes, our method outperforms the second best method UNO by more than 10%. And we are running additional experiment on 3 fine-grained dataset. The first is Oxford IIT PET. We see similar trend in here where the improvement is much higher. We also see the same trend on FGVC ER-curve dataset, and also the same trend on Stanford CART dataset. In here, we are showing ablation on different aspects of our solution. That means uncertainty guided temperature scaling, mixed pseudo-labeling, and we see that both of them, that means uncertainty guided temperature scaling and mixed pseudo-labeling, provides noticeable improvement to our method. And finally, in here, we assume that for all these experiments, the number of novel classes is known in advance. But as we mentioned at the beginning of the presentation, that we have a method to estimate the number of novel classes. Even if we use that method, our estimation method, and don't assume the number of novel classes is known in advance, we see that our method performs reasonably well. And on CIFAR-10 dataset, there is no performance drop. And also on tiny ImageNet, we don't see any noticeable drop. Only on CIFAR-100, we see some drop. But note that even this performance is higher than the current state of the art, which assumes the number of novel classes is known in advance. In here, first we obtain SimCLR feature. Even though we are using SimCLR features in here, this can be done with any self-supervised features. Then for k equals number of scene classes to a very large number n can be 1000 in here, and we are starting from number of scene classes because we know that the dataset at least contains that number of classes. We perform k-means clustering. Then after the k-means clustering is done, we'll compute the clustering accuracy on only the labeled samples, and we term that as accuracy labeled. But the k-means clustering is not perfect, and some of the label samples will be misclassified. So we reassign the wrongly assigned label samples to the nearest label cluster based on their distance. Then we compute the clustering accuracy again, and we call that actually accuracy reassign. We take the average between these two accuracies, and we pick the k with the best accuracy and call that is the total number of class present in that dataset. Now, if we look at the result, we see that on these 4 datasets, CIFAR-10, CIFAR-100, ImageNet 100, and tiny ImageNet, our number of total class estimation is reasonable, and we perform and we don't see any okay, this is fine, reasonable. But can our method work in a situation where we don't have that information? To answer that question, we make a simple modification to our method, where we train our model with uniform class distribution prior for certain warm-up epochs. After that, we obtain posterior class distribution from the trained model. That means we run inference on the unlabeled data. Then for iteration from M to E, that means end of the training, we basically use the latest posterior class distribution as our prior class distribution and basically train our model. And train our model. Then after every P iterations, we'll basically generate the posterior class distributions again to update our prior. Here are our results. In here, we are showing results on CIFAR-100 dataset with 50% classes and novel. Even though CIFAR-100 itself is a balanced dataset, for this experiment, we create imbalance in the CIFAR-100 dataset. We are showing results with 2 imbalance factor. Both are exponential with imbalance factor 10 and 20. And we see that given the data is imbalanced, if we use uniform class distribution prior, the performance we are getting is 38% for the experiment with imbalance factor 10. But if we use the ground truth class distribution prior, that means we know the imbalance, the exact imbalance, the performance improves. So it kind of validates that our method can effectively take advantage of the arbitrary class distribution prior if we have access to that. And now the last row is showing the most important result. That means what if we don't have access to the ground truth class distribution prior and we estimate it using previously described estimation method. Even in this case, we see that the performance is reasonable for both imbalance factor, and it outperforms just using the uniform class distribution prior. So this shows that our method can be applied to any situation where we don't know the class distribution prior in advance. In here, we extend our method to solve a simpler but a related problem, that is novel class discovery. For this problem, the assumption is that the unlabeled data only contain novel class samples. In our case, we are assuming that the unlabeled data can contain samples from both novel classes and known classes. So to adapt our method for this problem, we will generate pseudo-labels only for the novel classes. Now if we look at the results on CIFAR 100 dataset with 50% novel classes, we notice that even for this problem, our method outperforms the current state of the art by a significant margin. Here is our analysis of our, here is another analysis of our method where we are trying to see the sensitivity to the novel class estimation error. So even though we have our method for estimating the number of novel classes, we wanted to see that how sensitive our method is to the error of that novel class estimation method. And we see that even for both the case of overestimation and underestimation, there is no sudden drop in performance, and the method performs reasonably well on CIFAR 100 dataset. And in here we are showing another analysis. For most of our work, we assume that 50% classes as known and 50% classes as novel. What if we vary the percentage of novel classes? So this left plot is showing the performance on thin classes with different percentage of novel classes, and we see that our method performs reasonably well. And on if the percentage of novel class is very high, that means number of thin class is very low, the performance on thin class goes higher, which is expected because the task for thin class classification is easier now. We see a predictable pattern for novel class performance. The performance of novel classes goes down as we increase the percentage of the novel classes, and the overall performance is predictable as well. So in summary, in this work, we propose a streamlined solution for open-wall semi-supervised learning where we are using a single training objective. We proposed a simple method for estimating the number of novel classes. We can naturally handle arbitrary class distribution, and it can be extended to solve novel class discovery task as well. And our method outperforms current state of the art on multiple benchmark datasets. Thank you all for listening. Our code is available here.